After all this time philosophizing about writer's block and philosophizing about networks and LPs and the simplex method and talking about equality constraints and duality, and then finally coming up with some way of associating all of the machinery of the simplex method with a graph, with parts of a graph, so that we can use the graph only to talk about solving these network flow problems. Finally, it's time that we talk about making progress, about what is a pivot in this conceptualization of the simplex method using only the graph. And I think it's been about 2.5 hours of lectures so far to get to this point, so maybe it's about time for a recap. So in the previous lectures, or actually over the past 2 lectures, we saw that what we could do was model the complete state of the simplex method on one of these minimum cost network flow problems. What happened there? Using only a graph by associating labels with vertices and edges of a copy of my graph. And we can then talk about things in graph theoretic terms. We can talk about the basis of our problem as a spanning tree. So just to go through the terminology and the notation that we're going to use, which we've been building up over the past 2 lectures. First, like I mentioned back in the first lecture in the sequence, we will represent these instances using 2 parallel visualizations. One containing the original input, so this is the original input. And this is the state of the problem as it arrived. Things like the supply and demand at each vertex, the cost of using each edge. This will be our working data, and it will change over the course of the algorithm, whereas this will not. In a sense, what we're going to use this right-hand pane for is basically a way of representing, of visualizing a simplex dictionary, but strictly using a graph. And so the first thing we want to visualize is, what is the basis? And we'll write the basis out. The basis is a spanning tree. So if I have n vertices, I'll have n-1 edges in my spanning tree, which will be connected and acyclic. And remember that the word spanning tree refers to a spanning tree of the underlying undirected graph, because the term tree doesn't really apply as much in a directed sense. So the basis will be these edges highlighted in red, and it will be a spanning tree of the underlying undirected graph. We will choose one vertex to be a special vertex, and in this course we'll always choose vertex A, and we'll call that vertex the root of the spanning tree. So as you might recall from an algorithms course, a graph can have a spanning tree, and a tree doesn't require a root. It would be called a free tree in that case. But for a variety of reasons, one of which is to make computing the dual values easier, we're going to choose a vertex and forcibly make it the root of our spanning tree. And it will then receive special treatment. And so we're going to shade the vertex in purple on our visualizations, and if we ever need to look at an LP formulation directly, we'll also shade that entire row of the linear program in purple to indicate that it corresponds to the root vertex. Now, every basic edge, so my basis are the edges of these spanning trees, every basic edge will have an associated optimization variable, which may be non-zero. We expect that the values of the optimization variables for non-basic edges will, of course, always equal 0, because only basic variables can be non-zero in our usual interpretation of the simplex method. So if I look at all of my basic edges, each one will have an associated optimization variable, so there's xed, and we refer to the value of those optimization variables as the primal flow value for that edge. And of course, as the slide is pointing out, there are optimization variables for every edge. We only care about the ones for basic edges because all of the other ones are equal to 0. Additionally, each vertex, so if I look at vertex G or vertex F, each vertex will have an associated dual variable. I usually use the term dual optimization variable, so it'll be the variable Y corresponding to a particular constraint of my primal LP. And we know that the constraints of the primal LP correspond to the balance of one particular vertex, and therefore it shouldn't surprise us that the dual variables associated with those constraints are associated with each vertex. And so this, for example, would be the value of YG, and here would be YH. And on the right-hand pane, we're going to represent our dual optimization variables as labels on the corresponding vertex. And we also know that there is an intuitive interpretation of those dual optimization variables. And I guess one other note, which is that because we deleted the constraint corresponding to the root vertex in our primal LP, there actually is really no dual optimization variable for A. So we're going to invent one, make up a phantom phony dual optimization variable called YA, and just set that to always equal 0. Once we've done that, as we saw in the previous lecture, we have a way of determining the values of all other dual optimization variables given a particular spanning tree. And it turns out that they have a great intuitive interpretation, which is the value of a particular dual optimization variable, so this would be the value of YD, is the total cost of shipping 1 unit of flow from the root along the basic edges to that vertex, to vertex D. And so we can see that it costs 1 unit to go from A to E and 2 units to go from E to D, for a total cost of 3. Keeping in mind that if for some reason I ever have to go the wrong way along an edge, that we assume that moving flow in the opposite direction of an edge's normal direction also negates the cost of moving that flow. So moving flow from A to F would cost 1 unit to go from A to E, and then negative 2 units to go from E to F, for a total cost of negative 1. And that's what this says, yep. Now, in terms of the dual problem, there are also these dual slack variables, one for each edge, and they are paired up with the primal optimization variables XUV. We spent quite a bit of time over the first couple of parts talking about the fact that there are no primal slack variables. Because of the way the primal problem is defined, if we were to introduce these slack variables, we usually call them W, if we were to introduce these W variables, they would be meaningless. They would be ballast. They would be placeholders. And so we don't. But the dual problem does have both optimization variables and slack variables. The optimization variables are these Y values associated with each vertex, and the dual slack variables are associated with each edge. Just like with the primal variables, there is a dual slack variable for every single arc in the graph. However, if the arc is basic, then by complementary slackness, so if the arc is basic, then its x value could be non-zero, and by complementary slackness, the variable ZIH will be non-basic in the dual if the arc IH is basic in the primal, and that means that for every basic arc, I can assume that the dual slack variable is always equal to 0. And so complementarily to the way we're drawing the primal flow values, we therefore don't need to worry about any of the dual slack values for basic edges. So we're only going to draw the slack variables, the dual slack variables for the non-basic edges. And so, of course, here are non-basic edges where we know that the flow is 0, and the labels we attach to non-basic edges will therefore be the dual slack value for that edge. So combining everything together, we now have a pretty busy diagram. We've got our vertices, we've got our arcs, we've got our basic arcs, which are in red, our primal flows, which are the labels on the basic arcs, our dual slack values, which are the labels on the non-basic arcs, and then finally our dual optimization variables, which are the labels on vertices. So a flow is said to be primal feasible if every single primal flow value is non-negative. And we can see here, this flow is not primal feasible. Recall that the interpretation of a negative primal flow value, like this one, is normally a primal flow means how many units of flow are being transferred across the edge respecting its direction. So this one here would be 5 units from F to I. When I look at a negative one, what I'm really saying is, when I say send negative 3 from E to D, I'm actually saying send 3 from D to E, but just send it in the wrong direction across the edge. And of course, that's not feasible. The edges have directions for a reason. And so a negative value here means we're sending flow in the wrong direction, which isn't allowed, and therefore the flow is not primal feasible. A flow is said to be dual feasible if, when I look at all of the dual slack variables, they are all non-negative. And so here we can see this flow is also not dual feasible. It's got negative values on some of the dual slack variables. We spent some time talking about the interpretation of these dual slack variables. Basically, if we look at, let's say, this one here, what this is telling us is that it would cost 7 units less if I were to ship flow to vertex I via vertex D instead of via the current path, which would use this edge Fi. So the value of a dual slack variable is how much the cost of the of shipping would increase if I used that arc instead. So another example would be if I were to use this arc here to get flow to G, I'd be paying 28 units more than whatever I'm already doing to get flow to G. And that's one reason why I don't want to use this arc. It would cost too much. On the other hand, I might save some money by using this arc. And that means that if I want to find the minimum cost flow, this isn't really the best basis to do it. I might want to use a basis that includes this arc here. And so it shouldn't surprise us that this is the mark of dual infeasibility. A negative dual slack value means I'm not at an optimal solution yet. I'm dual infeasible. So a flow is said to be optimal if it is both primal and dual feasible. And remember that primal and dual feasibility depend only on the values attached to the edges. So this is not primal feasible, and it's also not dual feasible. But a flow is optimal if it is both. There is no requirement that the dual optimization variables be positive or negative. They can be anything. It turns out that they are unconstrained. And so, okay, now we're going to walk through examples of each. This flow is neither primal nor dual feasible. Negative value there, negative value there. Now, because it turns out that the procedure we're about to develop really requires us to notice these infeasible values, so negative flows or negative dual slack values, from this point forward, every time we typeset a diagram in this form, I am going to put the infeasible values in. It says we will typeset them. We, I think that's the usual royal we from math. I feel sort of bad giving we credit for this. I will do it. After all this time, I will be typesetting them, damn it. We will typeset them. You don't get any credit for this typesetting. Anytime we have a negative number, I'll put it in blue and I'll bold it. Hopefully that makes it more noticeable, so it's much easier to notice when a particular basis is primal or dual infeasible. And this basis is neither primal nor dual feasible because we've got negatives on both basic and non-basic edges. So here's an example of a flow that is feasible. I really should have said primal there. This is primal feasible, but not optimal. And the way we know that is, well, okay, all of these are positive, so that's good. Notice there's no blue on basic edges, but I have a negative value here. So it's not dual feasible, and unless it's both primal and dual feasible, it's not optimal. Therefore, it's primal feasible, but it's not optimal. Okay, so the question is going to be basically, what do we do to go from this to an optimal flow? And what we have here, unlike what we were talking about for most of the previous lecture, is we have a primal feasible flow. We've got something that does respect all of the edge directions and is balanced. It just doesn't cost little enough. So it is a solution to our problem. This is feasible in the sense that we're sending flows in such a way that all supplies and demands are balanced, and we're never sending flow in the wrong direction. The issue is we might have a way of saving some money, find some way of shipping flow such that we save money by shipping it across lower cost arcs. So it is primal feasible, but it's not dual feasible because there's ways of saving money. I want to find a way of making it dual feasible while, of course, retaining primal feasibility. And if you think about that sentence, that paragraph, that sounds exactly like the definition of what we want to do during a pivot in the simplex method. And of course, we now know it's of course going to be a primal pivot. But if we think back to May, what was it that we were doing in May when we derived the initial pivoting procedure for the dictionary-based simplex method? Well, we take a look at our dictionary. It's feasible. All of our basic variables are non-negative, and yet there is a positive objective coefficient, a way of increasing our objective value so it's not optimal. We now look back and realize that also is the same as saying that it's not dual feasible. Here, we have a feasible way of sending flow around the network. We just don't have one that minimizes cost. There's a way of saving money. So these two arcs in particular are not dual feasible. So what is the pivoting procedure? I am a really big fan of taking an intuitionistic or naturalistic or whatever approach to teaching everything, and that's first year programming up to this fourth year course. Honestly, I don't think it's very productive to just read you the riot act here, to say, here's a bunch of rules. Let's instead of just going backwards saying, here's what a primal pivot is, now let's figure out why it works. Instead of going backwards, let's go forwards. We know a lot by this point in the course. We are at the end of a fourth year or graduate level linear programming course. We have learned a lot about linear programming from lots of different facets. We've seen it the dictionary-based way. We've seen it from the linear algebraic way. We've now derived most of the network-based way. Maybe we could deduce what a pivot has to look like without actually just just reading about it and then working backwards. So what can we deduce about a pivot? So I think we can use some facts that we've already learned about pivoting in the simplex method and about what a basis is and about what basic variables are to try and figure out what we need to do. So here's some observations. Okay, the first one is our basis is a collection of edges. And of course, what that should tell us is that if I want to perform a pivot, what we normally do when we perform pivots in the simplex method is we remove one thing from our basis and add something else. Or maybe if we want to think about it in reverse, something enters the basis and something leaves. If our basis is a collection of edges, I should expect that any pivot will involve an entering edge and a leaving edge, or an entering arc and a leaving arc. We know when we perform pivots in the regular simplex method that we choose an entering variable. We choose it in a dictionary-based method from our objective row, but it's a variable that is dual infeasible. And we remember by now, from what we know about duality in the revised simplex method and everything else, looking back on the dictionary-based method, we realize that a variable that has a positive objective coefficient in the dictionary is one that is dual infeasible. And so if we think about that in terms of our network simplex method, what that tells us is my pivot will involve some arc that enters the basis and is dual infeasible. Okay, so how about this arc here? Okay, this arc will enter the basis. And another arc will have to leave. Why do I know that an arc has to leave? Well, one of the reasons is that I know that my spanning tree always has to have this size, this number of edges in it. And clearly, I haven't added vertices to my graph. So if I add an edge to my spanning tree, something has to give. I have to delete one edge from my spanning tree. It'll be my leaving arc. The question is, how do I find it? So in our dictionary, we have some idea of how to find it. We walk down the entire column of the dictionary. I'll observe that if we were to do the analogous thing here, we might be looking at every single vertex because each row of my LP is one vertex, is the balance constraint for one vertex. I might be able to observe that there are some vertices that clearly will not be affected by adding this edge. So if I add this edge, there is no way I'm going to want to remove this one. Because if I remove this one, the resulting basis will not be connected. It won't be a spanning tree. So you might be able to observe that we don't need the same amount of logic we would use in the dictionary-based method of walking through the entire LP. I may only need to consider certain constraints. In particular, the big invariant I want to preserve here is I want to make sure that when I'm done, the basis I end up with is still a tree, which means I can eliminate a lot of choices for my leaving arc. In particular, I can't get rid of this one because it would disconnect the tree. Can't get rid of this one, can't get rid of this one, can't get rid of this one or this one. And what does that leave us? Well, actually, it seems like it leaves us only these edges here. So if I add this edge to my graph, then the only edges that are candidates for my leaving arc are things that wouldn't disconnect the result. Now, one property of trees you might remember from CSC 225, if I have a spanning tree of a graph and I add one edge, I'm guaranteed to create a cycle. And hey, there's a cycle. Look at that. And once I have a cycle, maybe you can agree, if I delete any one edge from that cycle, that is not going to disconnect the result because there's always a way of getting to every vertex using whatever's left over of the cycle. Now, of course, it might not result in the basis being feasible, but certainly any of the edges in this cycle I could delete and I could still have a spanning tree when I'm done. That's our next deduction. So the basis must be a spanning tree, which means if I add a new edge to it, I will always create a cycle. The leaving edge has to be part of the same cycle because if I delete any other part of the spanning tree, I'm going to disconnect the tree. And the reason the leaving edge has to be part of the cycle is because I want the basis to be a tree when I'm done. I want it to still be connected. And then finally, the new basis, whatever I end up with when I'm done deleting my leaving arc, the new basis must be feasible. So I have to find a way of choosing my leaving arc such that when I'm done, I have a primal feasible basis. Ideally, when I'm done, I've also decreased my objective value. I've decreased the total cost of the flow. That's how I make progress. But I should be aware, given what I know about the simplex method, that I suppose it is possible to perform a pivot that doesn't lower the minimum cost. It would be the analogy of a degenerate pivot. But I may have to do that sometimes. But certainly, I want to make sure that when I'm done, I still have primal feasibility. I still have a non-negative flow across every arc. If I started with primal feasibility, I should end up with primal feasibility. All right, so in this case, first, what could I choose as my entering arc? On this example, I could choose this arc here, or I could choose this arc here. And we might know by now that there's probably some nuance to the choice, but that would be the domain of a pivot selection rule, something that we already know has some complexity to it. There are pivot selection rules that are performance-oriented. There are pivot selection rules that are more utility-oriented, like Bland's rule, that would choose a variable based on some predefined ordering of variables. So maybe we could say it's reasonable that we don't care exactly which one that I choose, only that I'm going to choose one of these two dual infeasible arcs to enter the basis. So suppose for now, we'll actually try the other choice in a few minutes, suppose for now we choose arc ED. If I do that, I'm going to end up with a cycle. I'm going to end up specifically with this cycle here. EDCB. Notice that this, when I use the word cycle, I'm referring to a cycle in the undirected graph. Just like with a spanning tree, a lot of our definitions are actually undirected graph definitions. This is not a cycle in the directed sense, because I can't actually travel all the way from E back to E, use it with my edge directions being respected. If I use basic edges only, I'd have to go across this edge in reverse. But it is still a cycle because it overconnects the spanning tree. We've defined our spanning tree in undirected terms, so it's reasonable that when we define connectivity and the cycles that are produced by adding new edges, we define those in undirected terms as well. So we create this cycle here. Our leaving arc therefore has to break this cycle. So logically, we probably don't want this to be our leaving arc because this was our entering arc. So our leaving arc has to be one of these things, one of these three other edges in the cycle. It does not have to be any of the other arcs in the basis. This is one more reason why having a graph theoretic interpretation is helpful, because I add my entering arc and I go find a cycle using some traversal algorithm or something else. Then, ideally, if the cycle is small, I don't have to look at every other variable, which might be the case in some dictionary-based method. So let's talk about the cycle in an abstract sense. Before we go back to that example, let's just talk about resolving a cycle in general. Suppose that my spanning tree was all of these red edges, and then I decided that the blue edge would become my entering arc. Now what that means is that when I started, the blue edge had zero flow across it. And my goal, if the blue edge is supposed to enter the basis, I mean, the whole reason I chose this blue edge, if we look back here, is that I decided to add this arc because it would save me money. Because there's a way of saving cost by using this arc instead of some other arc. So clearly my goal has to be that I want to eventually push some number of units of flow, K I guess. I want to push some flow across that edge. In other words, I want to increase my entering arc's flow from 0 to a positive value. Not indeed unlike what I would be doing in the simplex method on any other pivot. When I'm choosing an entering variable, my goal is to increase it from 0, to add it to the basis. Okay, so the flow on this blue edge was previously 0 because it was non-basic. But I want to increase it to some positive value. But I need to make sure that first I choose a leaving arc, but also that when I've adjusted the flow here, clearly if I were to send 10 units this way, I have to make sure that, well, if V was balanced before and I give it 10 new units, I guess I have to send 10 units outwards to make sure that V stays balanced. Keep in mind that just like any other pivoting procedure, we're going to design this procedure assuming that my basis was primal feasible and balanced to begin with. If it was balanced to begin with, then the flow along all of the basic edges when I started does put all of the vertices into equilibrium. So if I send any flow across this edge, I'm going to have to find some way of getting rid of it. But similarly, if I choose a leaving arc and I send no flow along the leaving arc, I only need to find some way of making up for all that flow that is suddenly missing. And what I'll discover is that notice how inside this cycle, some edges point in one direction, some edges point in the other. There is a way that, because of the requirement to maintain balance, there is a way I can derive to determine exactly how much I have to adjust the flow on each edge to allow me to increase the flow along this edge. And the change that I will perform might be negative in some cases, and it turns out that that will give me the condition that tells me how much I can increase the value K. All right, so before I did the pivot, when I've chosen my entering arc, all of these edges already have some flow value over them because they're basic edges. I suppose the value could be 0, but they're basic edges. They could have some flow over them. Now, suppose that I choose to increase this to some number. I think I'm going to use T here, not K. Suppose I choose to push T units of flow from V6 to V1. I want to increase this number as much as possible. If I do that, then V1 already is in equilibrium, which means I have to make sure that I push any T units that come in get sent right back out again. That means the amount of flow across this edge will now be F1 plus T. But that isn't itself a problem, because as long as t is positive, this will still be feasible if I just add t to it. Okay, but now what happens? Okay, so now V2 has too many units of flow. V2 now has, it previously was in equilibrium. It had zero supply. But I've now given it, for some reason, I've just forced in t units of flow. So now V2 has an extra t units of flow. Well, how do we resolve that? Well, we know the way these balancing problems usually work. We can't send the flow back along this edge. That's where it came in. So we have to send the flow out this way. But in this case, we're sending flow in the reverse direction. If I want to send t units of flow to V3, well, I'm sending it in the wrong direction across the arc. So I guess what I'm really doing is I'm saying to V3, please don't send me this number. Send me fewer units of flow. So really what I'm doing is changing the flow across this edge to be F2 minus t. Because now V2 is getting fewer units of flow from V3, which means when it gets extra from V1, it still balances to 0. And you can verify to yourself, whether you like the interpretation I just gave verbally, you can verify to yourself that certainly the incoming flows to this vertex do now still sum up to whatever they summed up to before. So whatever F1 plus F2 was before, put V2 into equilibrium, the plus t and minus t cancel out, and V2 is still in equilibrium. All right, well now V3 has a deficit of t. V3 still has a surplus, because V3 sent out t fewer units of flow, which means that V3 now has t extra units of flow on hand. It was in equilibrium before, and now it's got t extra. So I guess that means V3, maybe you're catching on to this, V3 has to send out t more units of flow to V4. Okay, but now V4 is not in equilibrium. Okay, maybe we're getting the idea. So what I want to do is I want to have V5 send me fewer units of flow. I mentioned in the last video that you probably were very uneasy about this idea of having flow go in the wrong direction along an edge. I mentioned that one interpretation of that is not that we're pushing flow in the wrong direction, but that when I say send negative t units, what I really mean is just send me t fewer units. That's really where this interpretation comes into play, is right here. Notice that I'm not actually sending t units backwards. I'm just telling V5, please don't send me as many units. Send me t fewer units of flow. Okay, so now V4 is now in equilibrium. V5 now has too much, and so it sends it on to V6. And we'll notice something sort of bizarre here, which is that notice how every vertex is now in equilibrium. I've sent t units out, and they've just sort of gone around in a circle, but every vertex is in equilibrium. Okay, so that I know that seems a little bit bizarre, that I've sort of invented new flow and just sent it back around and it goes back to itself. The reason that we're doing this is because I want to find a way of dropping the flow on some edge to 0. And if we notice, if my goal is to maintain feasibility, I sort of see what I have to do. So if I send t extra units along this arc, it doesn't matter how big t is. This arc will always be feasible because it was already feasible and I'm just adding a number to it. So it's not going to make it go negative. On the other hand, if t gets too big, this could go negative and so could this. And if these go negative, then we're in trouble. Then we've lost feasibility. And we know one thing about pivots, and that's that the whole system falls apart if we don't maintain feasibility. So I now am beginning to see what I might want to choose as my leaving arc. I might want to pick t to be large enough that one of these two things goes to 0. And then I choose that as my leaving arc. Once it's 0, I can make it non-basic. So let's now walk through this with the more professional looking diagrams on the slides. All right, first, what I'm going to do is I'm going to stratify the cycle into two different directions. So we'll notice that there are some edges that point in the same direction as my entering edge, and there are some edges that point in the opposite direction. In this case, the directions, we could call them counterclockwise and clockwise, but the important thing is if my entering arc points this way, any arc that points in the same direction with respect to the cycle is in one category, and the arcs that point in the opposite direction are in the other. I'm going to color them light blue and orange. And it turns out, if we look back at our previous example here, that it's the opposite direction edges that are going to be important to us. They are the ones where t ends up being subtracted. They are the ones that could go negative if t gets too big. Okay, so I've divided my edges up between, we could call them, I guess, colloquially, forwards and backwards. Forwards if they're in the same direction, and backwards if they're in the opposite direction with respect to the cycle. Now, let's consider what happens if I add t units of flow to my entering edge. Well, I end up with, well, okay, this slide is just telling me essentially that I have to, any adjustment I make to this edge has to be balanced out. I already talked about that. So I end up with this. If I move t units of flow across this edge, I have to adjust the flows across every other edge exactly this way to maintain the balance that I need. That maintains flow balance, the equilibrium of every vertex. Now, the other thing I want to maintain is feasibility. I want to make sure that when I'm done with this, that the flow across every edge is still non-negative. And I guess another ulterior motive is I want to make the flow along at least one arc go to 0, because then I can take that arc and remove it from the basis. And I notice the only arcs that could possibly go negative or 0 here are these ones, the ones in the opposite direction as the entering arc. And moreover, if one of them, which one will go negative first, I guess is my next question. And the answer is, well, whichever one had the smallest flow value. So if F4 was equal to 5 and F2 was equal to 10, well, clearly this is going to go negative first. As t gets bigger and bigger, this is going to go negative before this does. And so I might observe that the maximum value I can give to my variable t, such that all edges remain feasible, is I could set t to be equal to 5. And that would make this whole thing 0, which means I could pick this arc up and yank it out of the basis. And that is the basic logic, I guess, of our primal pivoting. We choose an arc to enter, and then we'll be guaranteed to have some cycle that forms. We stratify the edges between same direction and reverse direction, and then among all of the edges in the opposite direction, we are going to choose the one which has the smallest flow value currently. And the slides are currently still explaining this. I think they're even more long-winded than I am. Yeah, now here's the disclaimer about sending flow backwards. Okay, and so we end up with this point that we have to make sure these are the only two constraints that we care about, because these other ones can't go negative. And so, therefore, the maximum amount of flow that I can actually send will just be the maximum, or the minimum, the smaller of these two things. And yeah, this is actually a surprisingly long-winded way of explaining this. Somehow I feel like my explanation was surprisingly more concise than the slides. Anyway, in any event, regardless of which explanation you believe, we do now have enough information to perform some pivots. And so here is, I think, the procedure that we just derived. First, choose an entering arc, and we don't care how we're doing that right now. We just we use some pivot selection rule. The largest coefficient rule, for example, would choose an entering arc with the smallest negative dual slack value. So we now locate the cycle that was created by adding that edge to the basis. We then find all of the edges in that cycle that have an opposite direction to my entering arc with respect to the cycle. We then choose our leaving arc to be the opposite directed edge that has the smallest flow value, because it's the one that'll go negative first. And then we also sort of know, I guess I could do a more concrete example here. Suppose this has 6, this has 7, this has 4, this has 3, and this has 2. Okay, so what's our procedure? Well, first, we ignore all of the edges in the same direction as the entering edge, so they're completely ignored. And then we choose as our leaving arc the one that had the smallest flow across it among the opposite edges. So that would be 3. Okay, so we choose V5, V4 as our leaving arc. Now, the question is, how much flow am I really going to push across my entering arc? Well, we know that if we push any more than 3 units, this goes negative, and then we're in trouble. So we have to push exactly 3 units. Notice that the flow that we push across our entering arc ends up being exactly equal to the flow that was on our leaving arc, except now that flow goes in the opposite direction. All right, and so that would result in this going to 0, and then I can pull this arc out of the basis. That's what this step is saying. Set the flow value for my arc E to just match the flow out of my leaving arc L, and then perform the necessary adjustment for all of the other edges in the cycle. When it says to perform this adjustment, what it really means is basically just do this. Once I know the value of T, once I know that it equals 3, go through and then add 3 to all of the edges in the same direction and subtract 3 from all of the edges in the opposite direction. So there's a lot to do there, but I hope you can see all of the similarities between this and the pivoting operations we've been doing all semester. Notice there's also some nice stuff that we don't have to do, like computing ratios. So let's just start with a concrete version of the example, this abstract cycle from earlier, and then take that back to our bigger graph. And remember that what we're assuming here is, before I've added this edge to the basis, that this could be part of some larger feasible and balanced flow. The key thing is we don't care about all the other edges that are in the basis. All we care about is, at the beginning of this step, every vertex is in equilibrium if we take into account the current flow values. Okay, so I want to choose my arc v6, v1 to enter the basis. Also, yeah, okay, sorry. The slides are being extra emphatic about this. It doesn't matter what these numbers are. All we care about is, for whatever reason, this is a balanced and feasible flow. Because the numbers could be influenced by flow coming in or leaving to other vertices that aren't relevant to the cycle. Okay, so I first stratify my cycle in by forwards versus reverse. So all the edges in the same direction as the entering edge are blue. All of the edges in the opposite direction turn orange. That means that I just ignore all of these for now. For my leaving arc, I only care about the opposite directed edges. Then I choose my leaving arc to be the opposite directed edge with the smallest flow value. That will have value 6. And now my next step is I assign that flow value to my entering arc. And then I perform all of the necessary, adjustments. So I assign 6 units of flow to V6, V1. That means that there are now 11 units of flow here. So I always add flow if I'm going in the same direction as my entering arc. I subtract flow if I'm going in the opposite direction. So I add flow, so this is now 13. I subtract flow. This, of course, goes to 0, which is nice. And then I add flow here, which gives me 16. Okay, now I've got this 0 arc. I can now yank this out of the basis, giving me my brand new set of flow values. Notice also that I only actually have to adjust the flow values for the things inside the cycle, because all of these vertices are now in equilibrium again. So anything happening outside, any other vertices in the graph, they just stay put. All of the other flow values can be left as they are. So unlike in a dictionary-based simplex method where your pivot might have to modify every single thing in the dictionary, here, by having this graph theoretic characterization, we can really easily avoid modifying anything other than the flow values that are directly affected. So we'll let the slides go through it in their own time. So we choose, I guess this is a duplicate slide. Okay, so what we know is that if we increase the value of t to some positive number, then we need to make sure we don't make it too large, or else some of these things are going to go negative. So we will end up choosing this as our leaving arc. I think I got past this a bit. So now I set t to equal 6, and I adjust the flow to each arc. And when I'm done, my leaving arc will have a flow of 0, and therefore it can become non-basic. And that means I am now done my primal pivot. Now, to complete the pivot, I've already recomputed the flow values. Only the things in the cycle need new flow values computed. However, I also have to recompute the dual variable and slack values. And those can be affected in other ways. So I may have to do more recomputation for the dual values than I would for the primal values. So one thing I could do, of course, is I have a new basis now. I could just go and completely recompute the dual optimization and slack variables from scratch. We saw how to do that in the previous lecture. That would work. It turns out that there are some tricks we can do to save some time there. And maybe we'll see that if we try a pivot here. Here we're going to try the pivot adding the arc DI. The reason I'm going to use the arc DI is because it gives us a more exciting looking cycle. And we'll get to this arc eventually. So suppose I choose to add this as my entering arc. Okay, let's see if we can maybe work ahead of the slides and see through all of the steps that we're going to need here. So I know that if I've chosen my entering arc, I'm going to have a cycle when I'm done. So I think I can see the cycle. I think it's going to be this. Okay, it's going to be the cycle FIDCBE. Okay, there it is. So I'll just pull out only the flows for those edges so we can stare at them. I then break up the edges into two groups, the edges that are in the same direction as the entering arc. So the entering arc goes around the cycle this way. So any edge that's going around in the same direction is in the same is blue. I was going to say it's in the same direction, so that's sort of circular logic. But any edge that goes around the cycle the same way, we'll color that blue. It turns out that those will not constrain the value of my entering arc at all. Now put a bookmark here, because the fact that they won't constrain the value at all means that they'll be relevant to another definition we're going to need later, a particular thing that sometimes shows up while we're trying to find leaving variables in the simplex method. So I notice that the only arcs that are going to constrain the ultimate flow value are going to be the ones pointing in the opposite direction. So they have flow 5, 3, and 3. My leaving arc will be an arc chosen to have the minimum among those values. So it'll be either this or this. Notice that I have a tie, and that happens with computing leaving variables sometimes. We actually therefore know we're going to have a degenerate basic arc when we're done, which is one reason this was an interesting entering arc to choose. So I'll choose one arc to remove. I guess I'll just choose this, the arc CB, as my leaving arc, keeping in mind that your pivot selection rule would help you resolve a tie here. Okay, so I remove CB from the spanning tree. Now, before we go any further, I want to talk about that recomputation thing. So before I recompute my flows, I want to ask the question, if we go back to our initial example, so we have all these dual variables and dual slack variables. I know that I'm going to need to recompute them when I'm done. If I add this arc to the basis, my the cost to transport stuff to each vertex may change. Therefore, I should expect to have to modify my dual optimization variables and my dual slack variables because they're tied into cost. The question is, how much recomputation do I need? I mean, certainly I don't have to recompute, the value for A. So what do I need? Well, remember that we computed those dual optimization variables using our spanning tree, working from the root down the tree. So here's what I get if I delete my leaving arc from the tree. Notice how most of the spanning tree is still the same. In fact, everything below E here is exactly the same. The tree looks exactly the same below the node E. It's only this little piece that I've removed. Notice also that by removing it, of course, before I've added my entering arc, which will be this thing here, by removing it, I have disconnected part of the tree. And if we work backwards, if we think, okay, once I've added my entering arc, of course I'll have a tree again, which of my dual optimization variables will have changed? And I might realize that because I'm computing them from the root on down, all of the dual optimization variables for these vertices will be exactly the same. Because if I recompute them, the computation will be the same as it was before. The only vertices that will need dual optimization values recomputed are the ones that got separated. The ones that ended up in their own component when I deleted my leaving arc. So before I finish the pivot, it's useful to first remove the leaving arc, then figure out what got separated from the root, and then make a note to only recompute the dual optimization variables for those vertices. And notice that means I don't have to do very much recomputation. Even though the recomputation is actually pretty fast, it's linear time as we saw in the previous lecture, I don't have to recompute it for every vertex, just for the ones that got separated. And so, just to summarize with color, the dual variables for these vertices, the ones in purple, the ones that are still in the same component as the root, they will not change because everything's computed from the root on down. Only the orange ones will change. And so only those need to be recomputed when my pivot is done. Now, similarly, we also know that there are these dual slack variables, but the dual slack variables are computed based on the dual variables. So for example, there was an edge, I think there's an edge here, AE. So AE had some dual slack variable, but the dual slack variable only depends on the Y value. I shouldn't use X then. The dual slack variables only depends on these variables YE and YA. And because they don't change, any arc that connects strictly between vertices in the root component, the purple vertices, it does not need its dual slack variable recomputed either. So not only do I not have to recompute the dual optimization variables for the vertices that are not cut off from the root by my leaving arc, I don't have to recompute dual slack variables either unless the edge is incident to at least one of the things in the component that got cut off. So only those dual slack variables where one endpoint of the arc is incident to these vertices, these orange vertices, need to be recomputed. We'll actually see in the next lecture that in fact we don't even have to recompute all of those. Edges that are entirely trapped inside of the separated component don't need their dual slack variables recomputed. But for now, we'll just say we only have to recompute the dual optimization variables for the vertices that get separated by the leaving arc, and we only have to recompute dual slack variables for edges which have at least one endpoint attached to one of those orange vertices that got separated. Okay, now anyway, back to this pivot. So we chose our leaving arc. This was the leaving arc that we chose. Now, before we actually finish the pivot, we have to adjust our flow values. So my leaving arc had flow 3. So I first add 3 units of flow to my entering arc. And then I perform the adjustment necessary to compensate. So that would be subtract off. So everything in reverse direction gets the flow subtracted. So 5 goes to 2. Everything in the forward direction gets the flow added. So 3 goes to 6. 9 goes to 12. Let's see. Okay, so this 3 goes to 0, and this 3 here actually also goes to 0. So we subtract off from things in the opposite direction. We get this, and there we go. So we now have updated all of our flow values so that this, our leaving arc, is non-basic. It turns out this is also non-basic. This is also 0, but we will leave this one in the basis. We only need to have one leaving arc at a time. Our leaving arc can now be made non-basic. Our entering arc can now be added to the basis, and we now have this assurance that everything's still feasible. There are no flow values that went negative as a result, and the basis will definitely be a spanning tree. We broke the cycle that was created. And so we end up with this. Now, once we do all of the recomputation of dual variable and slack values, we end up with this state of our algorithm. And you might look at it and notice, wait, it's still not optimal. So also notice that this arc here, the basic arc DC, is degenerate, which we shouldn't be too surprised about. We know that degeneracy happens sometimes, and hopefully it's no big deal. So this is still not optimal because it's, although still primal feasible, it is not dual feasible. If you were to compute the total cost of this flow, you would observe that it is in fact less than the cost we had with the previous one before the pivot. We don't really need the total cost of the flow until the very end. Just like with the linear algebraic simplex method, during the method itself, we never actually need the objective value. The objective value just sort of falls out at the end. In any case, this is still not dual feasible. There is still at least one, I think only one, dual infeasible arc. Now, note, just in case you're reviewing this later, note that just because there's only one dual infeasible arc now doesn't mean that if I do one more pivot, I'll be optimal. Because we know that that we can perform a pivot, that could create all sorts of other dual infeasibilities somewhere. We just hope that over time, we reduce the number of steps left and eventually get to the optimal solution. If we keep reducing our objective value, we will eventually get to an optimal solution. Okay, so what we know is that this flow is primal feasible, but it's still not the lowest cost one. And so we want to perform more pivots until we get to a solution that's dual feasible. All right, so let's just do that. The next entering arc will be the arc ED. And it turns out, I should add, just as a meta note, if I had chosen ED, you may recall way back here when I chose my my pivot, I chose this arc for some reason. I actually had two choices. I could have chosen this one. It turns out that if I'd chosen this one, I wouldn't have been able to make as many interesting salient points. That's why I chose DI. I rigged the problem so I could make those points. Anyway, whatever. The chickens came home to roost. I have to choose ED as my entering arc now, so we'll do it. So I choose ED, and that creates this cycle here. It creates a cycle DIFE. Okay, so we, as usual, will label the edges of our cycle whether they're in forward or reverse direction. So this edge is forward, so it's blue. This edge is forward, so it's blue. This is the only edge in the reverse direction, which means by default, it is the only choice for leaving variable. I'll add that you might remember when you're working with, I guess I'll make up a new slide here. When you're running the primal simplex method with a dictionary and you choose some entering variable, let's say x3, and then I've got some other variables here, x4, x9, x10, x17. Remember that when you're choosing the leaving variable, what you're looking for are variables that have a negative coefficient on my entering variable. So x4 is, minus, I don't know, 7x3, x9 is plus 4x3, x10 is plus x3, x17 is minus 5x3. Notice that the signs of the coefficients tell us which things are candidates to be the leaving variable. And then we compute ratios as well to figure out what are legitimately candidates. These two things wouldn't be considered at all. Notice that a plus sign means that increasing my entering variable will not result in this thing going negative. If you think about it, that's sort of what's happening in a cycle too. The forward direction edges are sort of the plus signs. There's no way that I can increase flow across this edge and end up with this one going negative. So we ignore the edges in forward direction. We only consider edges in the opposite direction, which sort of correspond to negative signs when we're choosing our leaving arc. In any case, this has to be the leaving arc. There's only one choice. So the flow that I'm choosing will therefore have to be 2. So I push 2 units of flow this way. I then have to add the flow along the forward edges and subtract the flow from the reverse edges. So I end up, I think, with this. Okay, so that's going to be my, I guess I have to also work out the recomputation thing first. So just to be clear, so I'm going to want 8, 2, and 5 here. But before I do that, I have to observe that before I've added this entering arc, if I delete this leaving arc, notice that it's going to split the spanning tree up into 2 pieces, roughly these 2 pieces here. Whoops, there we go. So if I remove my leaving arc, which was this, here is how the spanning tree gets divided. And so I've got one component containing my root, and inside that component, none of my dual optimization variables or my dual slack variables need to be recomputed for edges that are entirely inside of this component. Any vertex outside the component, any of the orange vertices, will need their dual optimization values recomputed. Any edges that go between the 2 components will also need their dual slack values recomputed. Okay, anyway, to complete the pivot, yeah, I got ahead of myself here. We set this flow to be 2, which means this one goes to 0, this one goes to 5, and then this one goes to 8. Okay, and so we're now done. We pull this arc out of our basis, we add this arc to our basis, and we perform the recomputation. So hopefully you made a note of which vertices needed recomputation earlier. You now go and fully perform the recomputation. So we do that, and there we go. And notice that we now have another dual infeasible arc. So we're still not at an optimal solution. But maybe you agree that because in each of our previous 2 steps, we did modify a non-zero amount of flow. We were able to add more flow over an arc that was dual infeasible. So the fact that the arc was dual infeasible means we save money by using it. And because I ended up pushing a non-zero amount of flow across the arc, I've definitely saved money. So I've reduced my objective value, which means we are closer to the optimal solution. But we're not there yet. This is still dual infeasible. Okay, so I'll perform another pivot. So I choose my arc CB to be the entering arc. And now I end up with this cycle. Okay, so I have this cycle, and I look at all of the edges in the forward direction and reverse direction. So these 2 edges here are in the same direction as my entering arc, so we ignore them. That means that this has to be my leaving arc. That's the only choice. So what does that tell me about what I can do with my entering arc? Well, it tells me that my entering arc's flow has to be 12. Notice that unlike in the previous cases, 12 is a lot bigger than the other arcs in the cycle. Who cares? You only consider arcs that point in the reverse direction, and you choose the one with the smallest flow. So my flow value on this will go to 0, and my flow value here will go to 12, although I think just like before, I've got to first consider the disconnection. Right, yeah, so if I delete my leaving arc from the tree, if I just wipe this out, then I separate the graph into these 2 components. So there's this one and there's this one, and it looks like this. That means I will need a full recomputation of dual optimization variables for all of these. Well, that's too bad, but it's still only a linear time algorithm. When I've done the pivot, it's only linear time to do the recomputation. It's nice that by having this feature, I don't have to do a full recomputation unless it's actually necessary. And we'll see, we'll expand a bit on these recomputations in the next lecture, but we'll see that they're really not that big of a deal. It turns out the dual optimization variable for each vertex changes by exactly the same amount. So I have to recompute the dual optimization values for all of these vertices and the dual slack values for all of the arcs that are incident to these vertices. Now I want to complete the pivot. So I push 12 units along my entering arc, and then I subtract that flow from arcs in the opposite direction. So this goes to 0, this will go to 14, this will go to 12. All right. So I end up with this, and now I can pull out my 0-valued arc, and I can take it out of my basis. I can add my entering arc to the basis, and I end up with this. And if once I'm done the recomputation, I can observe that my dual slack values are all non-negative, and of course my primal flow is still feasible because I designed my pivoting procedure to always maintain feasibility, and that means this is an optimal solution. So notice how easy it is if I have everything up on the diagram here to identify an optimal solution. As long as everything on an edge is non-negative, then I'm good. Of course, these values can be negative. I don't care. It turns out it makes no difference because for the dual problem to be feasible, there are no non-negativity constraints on the y variables, and therefore it doesn't matter if they're negative or positive. As long as all of my z variables and all of my x variables are non-negative, then I am looking at a solution that is optimal, and this is that. And its total cost is 224. If you think back a few hours to the middle of part 1, when we talked about different flows on this exact example, we may recall that this was one of the ones we came up with, and now we have evidence that this flow is optimal. All right, so let's go go through a couple more examples of this. What we've derived is the primal network simplex method. It is a variant of the primal simplex method specialized for networks. So we'll go through one complete example on some new, even more hideous looking graph. So starting from this primal feasible flow above, let's find an optimal flow. Now, one question that should be natural to you at this point is, wait a minute, starting from this primal, how do we find a primal feasible flow? We've seen in the previous lectures tons of flows that are neither primal nor dual feasible. If you give me a graph and say, give me some primal feasible flow, what am I supposed to do? We need to know more about the dual simplex method to answer that. So we'll end up using a two-phase dual primal method to do that. We'll start from some arbitrary basis that is neither primal nor dual feasible, do some tricks, and end up with a primal feasible basis. And then we can run the primal simplex method. But for this lecture, suppose I hand you a primal feasible basis. Notice that everything is, all the flows are feasible. Therefore, I have a primal feasible basis. Find me an optimal flow. Okay, so my first step is I want to choose an entering arc. So what I'm going to do is I'm going to effectively use the largest coefficient method here. So the largest coefficient rule would say, among all of the possibilities for an entering arc, choose the one that has the smallest negative value. In other words, if we negate it, the largest, I guess. So that's the equivalent of Danzig's rule of the largest coefficient rule. So my entering arc will be Ji. Okay, so the first thing I do is I have to consider what cycle gets formed. It's this cycle here. So I end up with this cycle. Now notice that, sort of interestingly, although not a big deal, interestingly, every single edge in the cycle points in the reverse direction. There are no edges in the same direction. That's no big deal, because to choose a leaving arc, we look at the cycle, we look at the orange edges, the ones that point in the opposite direction as our entering arc, and we choose the one with the smallest flow. That would be this one. As a result, Gi is our leaving arc. The flow that gets assigned to Ji will be 2 units. And then to perform the adjustment, which I can't remember whether the adjustment has to happen immediately or whether it happens later. But to perform the adjustment, what we're going to have to do is we go around the cycle, and for all edges in the opposite orientation to our entering arc, we subtract. So I'd subtract 2 from here, I subtract 2 from here, I subtract 2 from here, and from, so this would be 12, and from here, and from here. All right. And then this example, I had to remind myself, this example is not going to do the thing where it colors the components, like orange and purple. That is something, hopefully, that you would understand how to do. So if I were to delete my leaving arc Gi, so that would be deleting this arc from the spanning tree, I could figure out that this is the separated component. All of these things are in the same component as the root. So the ones that would need a recomputation are all of these vertices over here. So I'll just keep crossing out the ones we don't recompute. These are the ones we recompute. Any arc incident to these vertices that crosses the bridge between components also needs its dual slack value recomputed. Okay, so I've done this adjustment and I've finished the pivot. Okay, so now Ji is in the basis, Gi is no longer in the basis, and my basis is still not dual feasible. It's looking a lot better, but we shouldn't get false hope. If I add this, it might turn out that I have a bunch of other dual infeasibilities that get created. So in this case, the total cost at the end of iteration 1 is 232. Not that we care that much, but I'm not done yet. I don't have an optimal solution. And although I keep saying this, I'm going to say it again. Isn't it great that I can decide whether I have an optimal solution just by glancing and looking for negative numbers? That's all I have to do. If all of the numbers on the edges are positive or 0, then we're good. But in this case, I've got one that's negative, so I keep going. All right, so predictably, this is my entering arc at the next iteration. So my entering arc is Fg. If I add it, I get this cycle here. Also, sort of interestingly, none of the other edges in the cycle point in the same direction as the entering arc. But we saw at the previous pivot that that was no big deal. As long as there are choices for my leaving edge, which there are, then I'm good. Although again, think back to that bookmark we placed a few slides ago. What happens if all of the edges are in the same direction? So that's one thing to keep in mind. But for now, it's not a big deal. My leaving arc will, of course, be EG, the one with the opposite oriented edge with the smallest flow, which means I'm going to push 5 units along this edge. I'm going to subtract 5 here, subtract 5 here, subtract 5 here, and subtract 5 here. So it'll be 5, 0, 4, 7, 5. And I finish the pivot. Okay, so there's 5, there's the 0. This is now a non-basic arc. 4, 7, 5. Okay, so it looks good. My total cost, wow, I actually reduced it quite a bit, is 162. But I'm not done yet. I now have this edge dual infeasible. There's still a way to save money. So I add this. My new entering arc will be GH. Okay, so my entering arc is GH, and what cycle does that create? So instead of letting the slides do it for us, let's see if we can figure it out this time. So GH, okay, it looks as if that creates this cycle here. All right, am I right? Yeah, there it is. Okay, so I add the arc GH and I want to choose a leaving variable. Now this time around, the cycle is actually sort of interesting. There are some edges in both orientations. There are some edges in the same direction as my entering arc, and there are some in the opposite. But we know that to choose our pivot, to choose our leaving arc, we only look at the edges in the opposite orientation. And so the leaving arc has to be JI, which is neat because we actually added JI. It was the entering arc a couple of iterations ago, but that happens in the simplex method sometimes. So my leaving arc will be JI, and I'm going to push 2 units of flow along GH. So I go and I subtract that from all the edges with the opposite orientation, so that's now 9. This will now be 0, and I add 2 to all of the edges with the same orientation. This will be 7, and this will be 7. Okay, so I finish the pivot, I recompute. Let's just also see what would be the disconnected component here. If I delete the arc JI, what component gets separated from the root? Well, actually, we've already been through this part. It's this. These vertices here would be separated. They are the ones that need a recomputation. So I finished the pivot. Let's just make sure my math worked out. That looks good. I finished the pivot, and for whatever reason, I'm still not done. I created some dual infeasibility down here, but my total cost did go down. So I've got another pivot left to do. My entering arc is going to be DC. Before we do the pivot, let's see what else we can work out. If my entering arc is DC, what is the cycle? Oh, it might be a big one. So I think my cycle will be this. All right, so all of this stuff. Okay, so I add the arc DC, I create this cycle here. I now choose the opposite oriented edge with the smallest flow, so it would be this one. FB will be my leaving arc. If I go back over here and I think, what does that disconnect? If I delete FB, then I disconnect the entire upper part of the graph. So this is now my separated component. Everything in here has to have its dual variable recomputed. Okay, so I assign 5 units to my arc DC. And I subtract 5 from all of the opposite oriented edges. That puts this at 0. I add 5 to all edges with the same orientation. So this would be 6, this would be 12, this would be 7, and this would be 15. All right, and I'm ready to complete my pivot. I remove this from the basis, I add this, and I end up here. And I've encountered an optimal solution. Everything, all of my dual slack variables, all of my primal flows, they are all non-negative. Therefore, I know beyond a shadow of a doubt that this is an optimal solution for this network, this minimum cost network flow problem, and the total cost is 141. Now, first off, I did the example by hand and on the slides to prove to you that even though the network looked hideous, it is possible to do everything by hand, even on an absolutely horrifying example like this. That said, obviously, in the more controlled setting of an exam or something, you would be expected to be able to perform complete pivots. If it was on a graph this big, you wouldn't likely be expected to do like 10 of them in a row. You might have to do one of them all the way through. But it is fair game to ask you to do every single step and to recompute all the values and to answer questions like, is the result optimal or not? In fact, I really hope that going through this example has proven to you that, in a sense, this network simplex method is sort of easier. There are lots of numbers to throw around, but compared to all the stuff that's stuck inside a dictionary, think about how many constraints this actually has. So there are, 11 vertices. That would mean a dictionary with a basis of size, well, in this case, it'll be a basis of size 10. If we added slack variables, there would be absolutely horrendous number of variables because there's 11 vertices, that's 11 constraints, plus some horrendous number of edges. I think the average degree of the graph is like 3. We might agree that the dictionary-based simplex method for this would be a nightmare. And yet, by having this graph theoretic interpretation, it's not so bad. There's still lots of numbers to throw around, but it's much more manageable. That doesn't just translate to human efficiency, that translates to computer efficiency as well. Now there's this question, which is that we've just derived the primal simplex method for networks, the primal network simplex method. But there's one loose end. So we know that when we take an arbitrary LP and solve it, if I say solve this LP, what I'm asking you to do is to determine the final status of the LP. Is it feasible and bounded? In which case, what is the optimal solution? Is it completely infeasible? Is there no feasible basis? Or finally, is it unbounded? Now, we know that that middle one of is it completely infeasible, we are not yet equipped to answer that question. question, because for today, I've said stuff like, here's a primal feasible basis. Now solve this LP starting from that. We don't yet know what it means for there to be no such thing. So we're not yet there. We'll see that in the next lecture. But I can answer the question about unboundedness. What does it mean for one of these problems to be unbounded? We should have some analog of that, because we can see unboundedness with the regular simplex method, and we might recall that we typically detect unboundedness when we've chosen our entering variable in the simplex method, and while we're trying to find a leaving variable, that's when we notice that something is wrong. Okay, so let's use that as our template. We know how we select entering and leaving variables in the network simplex method. We choose our entering arc, we locate, in the primal simplex method, we locate this cycle, and then we enumerate the choices for leaving variable. And they are going to be chosen from among these arcs pointing in reverse direction. Okay, so wait, what does it mean in the regular simplex method for something to be unbounded? Well, that means in your dictionary, you've chosen your entering variable to be, I don't know, x3, and you've got everything in the basis, so x6, x17, and maybe you observe that every single coefficient is positive. And we know that when that happens, that none of these put an upper bound on the value of x3. So x3, and therefore the objective function, can be increased without bound. And I mentioned earlier, I said, put a bookmark at this point, when I mentioned the fact that, in a sense, the sign of the coefficient is an analog of the direction of the edge in the cycle with respect to my entering arc. And that's why all of the edges in the same direction would never be a leaving arc, because there's no way that they can go to 0 as a result of increasing the flow here. And so we might already have some hint what it might mean to be unbounded. And in particular, we saw way back in the previous example, there were a few cases where we had these cycles where every single edge pointed in the opposite orientation. But we haven't yet seen an example of a cycle where every single edge pointed in the same orientation. And it turns out that that is our condition for unboundedness. So the question is, what would happen if we had this case? If the cycle was oriented entirely in the same direction, if it were literally a directed cycle? Well, in that case, if I push t extra units of flow here, then I would have to push t extra units of flow here and here and here. But none of these would ever go negative. I could push 20 million units of extra flow, or 20 billion, or whatever, and I would still be allowed to do this. There are some certainly metaphysical questions about where I'm getting all of that flow from. And what this is saying is, if there are no opposite-oriented edges, there is no bound on how big I can make this. And we know that because of why I chose my entering arc, so the goal of this flow problem was to save money. And I determined when I chose my entering arc that by pushing a bit of flow along this edge, I save some money. And that means that the more flow I push along the edge, the more money I save. And my goal is to minimize the amount of money I'm spending. So the more money I save, the better I'm doing with my objective function. What this is actually telling me is that if I just, let's use the analogy not of the flow being water in water pipes or oil in an oil pipeline. Suppose that I run a company that makes sofas. And when I'm pushing flow through the network, I'm actually putting a sofa on a truck and sending it to a different city. And the idea is, in a well-defined, in a well-behaved network, I might have a situation like this, which is that I make 5 sofas in city A, and city B needs 3 sofas, and city C needs 2 sofas. Okay, well then I send 2 to city C, and I send 3 to city B. Good, problem solved. That's my flow problem. I have 5 sofas, and I want to send them to 2 different cities. An aside that I didn't realize until I started on this ridiculous example, it turns out that if you have a flow, there are ways you can guarantee that you never end up with something illogical like sending 3.5 sofas. It turns out you can expect integer valued flow values for cases like this. So suppose that I'm sending sofas, and I, for some reason, work out that I save $10 every time I send a sofa this way. And I notice that I can send as many sofas as I want because they'll all get back to V6 eventually. And effectively, I get a profit of $10 every time I send a sofa on this tour around all 6 cities. So what I'll do is, I'm trying to get at this idea of why is this still logically unbounded? Because it doesn't make sense that I would have 20 billion sofas to send to city V1. How about this? I'll put one sofa on a truck and I will send it on a loop between all 6 cities over and over and over and over again. Every time it goes around the loop, I make a little bit of money. Wouldn't you agree that in a case like that, it makes less sense to try and worry about saving cost elsewhere and more to just send that one sofa forever around all 6 cities? I just keep making more and more money. For some reason, I'm able to make a profit sending flow all the way around and back again. And it turns out, in this case, if this situation ever occurs, and hopefully you're still staring at it and thinking it sounds completely illogical that you would make a profit by sending flow across an edge. And it is sort of illogical, but it could happen. If this situation ever occurs, then we have an unbounded flow problem. If ever you reach a point where, with respect to your entering arc, every other arc in the cycle has the same orientation as the entering arc, then you can push as much flow as you want all the way around the cycle. And because of why we chose the entering arc, there is this understanding that that means you save money every time you do so. You make money by just sending something all the way around and back again. So if you put one sofa on a truck and send it all the way around between all 6 cities, you've made money. And of course, that means the total profit is unbounded. Now, it's not a question of minimizing the cost. It's actually a question of now maximizing profit. You can be spending negative dollars to ship your sofas between cities. Now, obviously, there are some questions about when that would really happen in practice. So this question is resolving what I already said, which is, why is it that this situation results in unbounded flow? And the answer is, because we chose E as our entering arc, this arc here, that was the reason this arc was chosen was because it was dual infeasible. And dual infeasibility implies that I'll save money by using this arc instead. That means the more flow I push across the arc, the more money I save, or in a sense make, because of the old adage that, because of a theorem which states that a penny saved is a penny earned. So if I'm saving $10 by using this arc, I'm in a sense making $10. And so this is a more specific justification of what I've already said, but I feel like I'll just leave that there because I feel like I did. Oh, actually, I will fix it. I'll fix a typo. I think this is in reverse order. I'll fix that in the posted version. So here is an explanation of why technically what I just said has to imply unboundedness. I think, though, that the explanation verbally pretty much gets at the core of it. But in case you want a more technical explanation, there it is. It'll be in the posted version of the slides. Now, the question really that we should ask is, when will this actually happen in practice? So, like, why would it ever be practical for it to somehow be profitable to just send flow around in a circle infinitely? And the answer is actually spectacularly obvious. It just sort of like smacks us right in the face, which is, what if the cost of an edge is negative? And you should ask yourself the question, why reasonably would that ever be the case? And the answer is, it turns out there actually are economic applications where this could occur. There are cases where the use of a particular supply route could be subsidized, for example, for lots of reasons. That is to say, some outside force could artificially incentivize using a particular path over another one. So the government could, for example, to promote tourism or something, make it somehow more beneficial to travel to vertex E than to any other vertex by making that cost negative. That does actually happen. That can come up in economic applications. And if you're the person working out shipping economics for a company that makes sofas, and you notice that putting a sofa on a truck in vertex A and sending it around in a circle like this, as I'm sure you'll see, if I send the sofa around in a circle, I guess it costs me nothing. So I get $9 for sending it to vertex E. They pay me to send a sofa there. And then it costs me 8 and then 1. So I can send it all the way around in a circle and it costs nothing. So it turns out that having a negative weight edge is sufficient to create the conditions for this unboundedness to occur. Now, again, the reason I wanted to go through that long explanation of government subsidies or whatever is that you might stare at this and say, we shouldn't allow this. This is never going to happen in practice. Why would somebody pay you to use a transportation link? It can, in fact, happen even in practice, even in legitimate practical applications. So we should talk about why it would happen. On the other hand, it is worth noting, unless you have a negative weight edge, you shouldn't expect this to happen. Although there could be there's some funny degeneracies that occur. Unless your edges have a negative cost, you shouldn't have to worry about it. And that's one way. If I give you a network where all of the costs are positive, you can say emphatically, we're not going to see unboundedness here. So if I run the primal simplex method, what I'm eventually going to reveal is that the minimum cost flow problem is unbounded, that there is for some reason a way not only to save money, but to actually make an infinite profit by sending flow through this network. And I want to walk through the example in some detail. I want to actually do the pivots. Okay, so I choose my arc DI as the entering arc. I think there was a disclaimer here. Yeah, sorry about this. I should have been clear. The only difference between this network and the example we did earlier is this one edge. Everything else is the same. So we're going to do some of the pivots we already did pretty much the same way. But eventually we'll see this problem will become very manifest. Okay, so my entering arc is DI. Okay, so I add this. This example would be good practice just of the regular primal pivoting procedure. So I choose DI as my entering arc. That's going to create, I think it's going to be this cycle here. All right, I have some opposite directed edges. We actually did this exact pivot already. And so I choose this as my leaving arc. It gets set to 0. This gets set to 3. This gets set to 0. This gets set to 2. This gets set to 6. And this gets set to 12. All right. Okay, so I have this. Oh, whoops. Okay, sorry. So this will be my leaving arc. It could be either of these. For some reason, this time around, I chose DC as the leaving arc. Okay, so now I have this basis. Total cost is now $250. All right. So my entering arc now has to be ED. Okay, so I choose ED. I end up with this cycle here. We can see pretty obviously this is going to go to 0, this is going to go to 2, this is going to go to 5, and this is going to go to 8. There's my pivot. It's done. I now choose my arc DC, which of course left the basis just 2 pivots ago. I choose that as my entering arc. This is a bit of a slow burn, this example. I choose this. I end up with this cycle. This is still a nice, well-behaved cycle. We might recall having done this pivot earlier, so I certainly think choosing this as my earlier leaving arc would have been a better idea. So here I set this to be 12, I set this to be 12, I set this to be 14, and this goes to 0, and now I end up with this. Uh-oh, this arc has turned dual infeasible. That's the way of the simplex method telling me I can save some money now by using this arc instead. And here we notice we have a problem. So if I look at the cycle that gets created here, by adding the arc AE, I get a cycle of AEDCB. And I notice that every arc in that cycle has the same orientation as my entering arc. What that's telling me is that there is no bound whatsoever on exactly how many units I can send along this edge. Okay, but why does that imply unboundedness? For all of the talk about sofas and profit and infinite profit and subsidy, why does that imply unboundedness, Bill? Here's why. Let's look at what this means in the original graph. So I'm going to send 1 unit of flow. All I have to prove to you is that if I can make any money at all by sending something around the graph, clearly I could make more money by repeating that. So I'm going to send 1 unit of flow. If I send 1 unit of flow around this cycle, what happens? I get a profit of $9 for sending it to vertex E. It costs me $2 to send it to vertex D, which means that I now have a profit of $7. Okay, it cost me $4 to send it to vertex C, so I now have a profit of $3. It cost me another $1 to send it back to B. I now have a profit of $2. It cost me $1 to send it back to vertex A. So I put a sofa on a truck and I sent it all the way around these 5 cities on tour, and when it got back, I had a sofa, a truck, and $1. And so I say to the truck driver, just haul ass around the cycle again, and I get another $1. And if I keep sending that truck on that same circuit around all 5 cities, I can make as much money as I want. Now, it'll take a long time, depending on transport costs. Ideally, this is just economics advice. A good business strategy here is, as you get more and more profit, invest that profit into more trucks, and then send those trucks around on a circle. Actually, just buy more sofas and put them on the same truck. You can make as much money as you want if we have this situation. If there ever is a case where an edge has a negative cost, that doesn't inherently mean that the problem will be unbounded. But if you ever find a cycle where the total net cost comes to less than 0, you now have a way of printing money. You now have a way of generating infinite profit by just sending flow around that cycle in a loop. There is this question, though, which is, okay, so beyond any question about why this would ever occur, is it true that just because I have a negative weight edge, that automatically makes the problem unbounded? And the answer is no. An example would be, suppose I had this situation here. So here is vertex J. Okay, and it costs me negative $10, no, negative $1,000 to send something to vertex J. That means that if I send something to vertex J, I'm guaranteed to make some profit. But vertex J has a finite supply. Vertex J only has let's say, a deficit of 10, which means given the way vertex J, the more I look at it, it's a very strange looking J. Given the way vertex J is situated here, there is no way for flow to ever leave vertex J. And that means that the most flow I can ever send along this arc is 10 units. Because if I sent more than 10 units, balance would not be maintained. And of course, I can't send flow in reverse. Although if I did send flow in reverse, it would cost me $1,000. So this profit would be negated because sending flow in the wrong direction negates the cost. So there's no way I could leverage this negative weight edge to produce infinite profit. It's only if I get a cycle whose total cost is negative. But certainly you won't get such a cycle unless at least one arc has negative cost. Sorry, I keep saying negative weight. It's because I'm deep down underneath many layers of repression. I'm secretly a graph theorist, and I talk about edge-weighted graphs in my sleep and things. So if you have a cycle with net negative cost, then you can make infinite profit. Then the problem is unbounded. But that doesn't mean that the presence of a negative cost edge inherently makes the problem unbounded. Nor does it mean a negative cost edge being in a cycle is a problem either. So for example, suppose I had a cycle that looked like this. In fact, I'll even make it, we'll start with this. Okay, it costs $10,000 to transport one sofa out of vertex J. Although I get $1,000 for sending a sofa into vertex J, there is no way I could make a profit sending it around in a circle, because it would still cost way more to send it in a circle than the profit I could make off this one arc. In fact, I wouldn't make a profit unless the cost were lower than, so if I set this cost to $997, it's still not profitable to send a sofa around the cycle, because it would cost me 1,001 units to get the sofa from J to I, and then I'd get $1,000 back. So it would still cost me net $1 to get the sofa around in the circle. It's only if you have a cycle with net negative cost that you have an unbounded problem. So that is one, and it's worth considering, of course, that that's something we can identify graph theoretically. Before even running the network simplex method, you could just use a traversal algorithm to figure out if there is a negative cost cycle, and then decide if it's unbounded as a pre-processing step. But it also turns out, quite conveniently, that while you're running the primal network simplex method, if you ever encounter this situation, you can stop, you can say the problem is now unbounded, and I'm done. And that's the only place unboundedness can occur. For symmetry with the regular simplex method, the non-network simplex method, where we always detect unboundedness when we are finding our entering variable. So negative cost edges are the cause of unboundedness, but they don't necessarily cause unboundedness. But in any case, we have a way of detecting it. So what we've seen today is if I hand you a primal feasible basis, if I hand you a feasible flow, and it's not optimal, if there are negative dual slack variables, we can employ primal pivoting, the primal network simplex method, to produce the optimal solution. Now the next question, or I guess pair of questions, is what if I hand you a flow that is not primal feasible but is dual feasible? Well, we know by now that there's probably a solution in the form of the dual network simplex method and dual pivoting. And we want to learn that, not just because that allows us to solve problems that are not primal feasible but are dual feasible, but because the real thing we care about is if I hand you a network with no other information at all, if I say, here is a network, give me the optimal flow, you have to find a primal feasible basis somehow. If you just chose a random spanning tree, so I don't know, here's a random spanning tree. Actually, this is a sort of nice one. I like this one. Here's a nice sort of Hamiltonian style spanning tree, although it's not a Hamilton path necessarily because it's not directed. In this spanning tree, I'll bet this is not primal feasible or dual feasible. So the question is, if I hand you an arbitrary network, how do you solve the problem? How do you find a feasible basis? And to do that, we're going to do the same thing we've done in last week with the linear algebraic simplex method, which is use both methods together in series. First, use the dual simplex method to find a primal feasible basis, then use the primal network simplex method to find the optimal solution. So the next lecture is going to be about the dual network simplex method.